Let us begin our discussion of mechanical behavior with the natural point to start from, which is elastic deformations. And the first concept that we should recall from our ME 231 course is the concept of stress. Stress is something that has to do with the forces, or the loading that is applied to the structure. We might have forces, eventually moments and torques applied to a structure. Let's take an example. Let's consider a beam with a circular solid cross-section, and let's imagine that there's a torque, there is say a tensile or compressive force applied to it in addition to a possible bending moment. And the application of this loading will ultimately cause different states of stress at different points within the structure. And what we are interested in is to express the stress at a arbitrary point of the structure, let's say that point. So I'd like to write down or depict the state of stress at that point in the structure. And there are two ways with which we can do that that will serve us also, both of which will serve us to recall important features about the stress concept. The first way to depict it is to depict the stress geometrically. So I'm going to zoom onto that point and imagine that there is a tiny cube in the vicinity of that point. And if we zoom onto that point, that's how, say, the cube looks like. Okay. We will eventually need a coordinate system. Let us call this direction x, that direction is y, and the third direction is equal to z. So I am not looking at a structure which is in the form of a cube. I am looking at a point that's this point, and if you like, around the vicinity, in the vicinity of that point, I am taking a cube now, a very small region of material, and on that material I'm going to depict the components of the stress geometrically. And that's what I mean by geometrically, because it's based on this geometric description of a small region of material in the vicinity of the point I am interested in. So now there will be three normal stresses. And the definition, recall, is that, first of all, whenever I write a normal stress, I'm going to indicate it with sigma. So there is a plane with normal x. So on that plane, there will be a normal stress with index x. There's a plane with normal y, on which there will be a normal stress with stress equal to sigma y. And there is a plane with normal z, on which there will be a sigma z. Okay, so those are my normal stresses. Now, but just like the force in general on a surface will have components that are normal and tangential to the surface, the stress, which ultimately has to do with force per unit area, will also have components that are normal and tangential to the surface. So in this case, each surface has two tangential directions, with which there will be two related shear components of the stress. So whenever I write a shear stress, I will indicate it, we indicate it typically with tau, and the default direction has to do with, again, the coordinate direction. So the positive direction for the normal stress is on the plane with a normal that is in the positive x direction. The default direction is also sigma x. okay, the positive x direction. So on the plane with normal x, the default directions for shear will be along the remaining two coordinate directions. So there will be a shear stress that looks like this. And there will be another one which looks like that. Okay. So on each face, a similar argument eventually holds. On the plane with normal y, there will be a stress component which looks like this, and another one which eventually looks like that. Okay, so at this point, let me start actually calling them tau, because that's the notation that we are going to use for shear stresses. Okay, and on the plane with normal z, we will have a shear stress along that direction and also along the positive y direction. So that's another tau. Well, what is the naming convention for the stresses? Well, this depends to a certain extent on the preference of the person doing this, but ultimately it will not make a difference. Let us talk about our preference in this course. The way we're going to recall how to write the components of the shear stress is going to be as follows. So first of all, I will look at a plane. For instance, this plane. This plane is the plane with normal positive x. Therefore, in that direction, there is a normal stress sigma x. So the first index of the shear stress is going to indicate the component that is associated with the normal to the plane. So the component of the normal, the index of the normal stress, if you like. So the first index is going to be tau x. But that's just the first index, indicating that the shear stress has to do with the plane with normal x. The remaining index will indicate the actual direction of that shear stress component. So this one is associated with the plus y direction, so we'll put a y. And the other one is associated with the z direction, so we'll put a z. So as I do this, you may want to think about now, ahead of me, you may try to complete the indices before I write it. So what shall I have for the green components? So we are lying on the plane with normal y. So there's a normal stress sigma y. So that's the index that we can immediately attach to the shear stress. Okay. This already will eliminate a certain possibility for making an error when we are indicating the stress components. So immediately attaching the normal component index just puts us to a certain level of safety, if you like, with respect to making an error. So then the second index has to do with the direction, because something needs to distinguish this component of the shear stress from the other one. So this one is along x, the other one is along the z direction. So those are the components of the shear stress on the plane with normal y. And here, likewise, we're going to have a component. We're on the plane with normal z, so both of the shear stresses will have component z, and the second index indicates the direction. This one is y, and this one is x. Okay, so that's the way the stress is depicted geometrically. Now, remember, it goes without saying that on the surface that opposes, say, this one, there also needs to be stress components. Well, what are their values? And why does it have those values is a question that we can ask ourselves immediately. Why do we need to have stress components also on that surface? What should their values be? Okay, so go ahead and think about that question for a few minutes, just to just to recall what we have done in ME 231. But so the answer is, well, this infinitesimal cube of material, which serves to depict the stress geometrically, but ultimately it is a small piece of material. So this small piece of material, because this structure needs to be in equilibrium, also needs to be equilibrium. And equilibrium requires that the sum of the forces in all directions is equal to 0. And force is stress times area. So if the areas of the two faces are the same, the components of the force on each surface needs to be the same in magnitude but opposite in direction. So there is a sigma x in the opposing direction, tau xy in the opposing direction, tau xc in the opposing direction. Okay, so we're not depicting those unless we depict it in 2D. So just as a way of doing that, let me do a depiction in 2D. Omitting what has to do with the z direction. So there will be a sigma x, there will be a sigma y, and there is a sigma x there as well, sigma y there as well, and there will be a tau on the plane with normal x in the direction y, on the plane with normal y in the direction x. And the stress components on the opposing faces are equal in magnitude and opposite in direction. So that's going to be tau xy. This is going to be tau yx. Okay, so that's a 2D analogy without worrying about the third dimension. Okay, so that's our state of stress. Remember, there is a certain state of stress at a certain point in the structure, and that is what I am depicting. And I am emphasizing this concept of state of stress because it turns out that there is a unique state of stress at a point within a structure when it's loaded, but eventually we will see in our next topic that there are multiple ways of depicting that state of stress. This is the pictorial depiction of the state of stress with respect to a given picture. The picture is eventually decided by our coordinate system. So now, is there an alternative way of depicting the state of stress? Well, there is, and that is a, if you like, a mathematical depiction, which is a matrix form. So what we can do is we can take the components of the stress and put it into a matrix. We can do so because ultimately I see here 3 normal stresses and eventually 6 shear stresses. And if I think of the index x as being 1, y, 2, z, 3, I see components like 1, 3, 1, 2, 2, 1, etc. So these naturally look like components of a matrix to me. And this is going to be eventually a 3 by 3 matrix. And on the diagonal, I will prefer to put the normal stresses. So this is like 1, 1. We're not repeating x. So the normal stresses go on the diagonal, sigma x, sigma y, sigma z. And the shear stresses go off diagonal. And again, we're going to think of x as 1, y as 2, z as 3. So it's going to be tau x, y, 1, 2, and then 1, 3, which is xz. And then tau yx, 2, 1, 2, 2, 2, 3, yz, and then 3, 1, zx, 3, 2, zy, and sigma z, 3, 3. Okay. So now when I look at the depiction of the stress, representation of the stress in matrix form, in a mathematical form, if you like, well, I see 9 components. And now our next question is, does the stress have really 9 components? In other words, if I want to know the full state of stress at a point in a loaded structure, do you need to provide me with all the 9 components? Or is it sufficient perhaps that you provide less? Okay. So if you've thought about that question for a few seconds, then the answer is as follows. Well, first of all, let's remember, why do we have stress components on opposing faces as well? Well, we do because it's a small piece from the material in the vicinity of the point I'm considering, and this material needs to satisfy equilibrium with respect to forces. But remember, it also needs to satisfy equilibrium with respect to moments about any point that lies within or outside of that tiny infinitesimal cube of material. And that requires more than having equal and opposite magnitude stresses on each face. What it also requires is that the shear stresses on neighboring planes, so if you like in this case tau yx and tau xy, they should actually be equal, not only in magnitude but also in sign. So tau yx needs to be the same in magnitude and sign as tau xy, tau yz as tau zy, tau zx as tau xz. So these are actually equal. Okay, so that's an equality sign, that's an equality sign, and that is an equality sign. So in other words, the stress looks like a 3 by 3 matrix, but it actually does not have 9 independent components. In other words, you don't have to provide all the 9 components to know what is going on at a point in terms of state of stress. All you need to supply is 6 components, 6 independent components, and that is because the stress is actually a symmetric matrix. So this is the concept of state of stress at a point, which has to do with forces. Now, when you subject a material to a certain state of stress, eventually we also know that it is going to deform. So that deformation, the calculation of that deformation will eventually depend on the material behavior itself. In this discussion, we are going to eventually assume elastic deformations. But deformation will occur whether or not deformations are elastic. So let's first go ahead and think about or recall how we characterize the state of deformation. Okay, so we are going to talk about the concept or recall the concept of strain, which has to do with deformations. And let us actually quickly recall deformations or concept of strain in the context of a quick example. And in that example, let us take a plate that lies in the xy plane. So we're going to omit whatever has to do with the z-axis. So that's our x direction, that's our y direction. And let us imagine that initially we have a plate that is of size 1 meter by 1 meter. All the units are in meters. Okay. And what we are going to do is we're going to apply certain forces, a stress distribution on the, if you like, on the surfaces of this plate. We're not depicting the third direction. And this will cause the plate to deform. Initially it is square, and after deformation, let us say that it looks as follows. Okay, and we know, let's say, the exact amount through which deformation occurs. So in particular, this distance is 5 times 10 to the minus 5 meters. Of course, I am exaggerating the extent of deformation. And the distance in the distance traveled in the horizontal direction is 2 times 10 to the minus 5. Okay. Good. And the question is, well, what are the strains in this structure? Now, the first thing we can recall is that the strain will also have normal and shear components. The normal strains will be indicated with epsilon, and the shear strains will be indicated with gamma. Okay, and therefore we will have a total of 3 normal strains: epsilon x, epsilon y, epsilon z, and eventually we will have 6 strain components: gamma xy, gamma xz, gamma yz, as well as gamma yx, gamma zx, and gamma zy. Okay, so let's extend that list with this dotted line. All right, and now the question is, what are the components of the strain in this problem? Now, first of all, we're looking at a two-dimensional deformation. I am implicitly assuming that nothing happens along the z direction, which is the out-of-plane direction. And therefore, anything that has to do with the z-axis in this particular case will have essentially correspond to 0 strain. So epsilon z will be 0, gamma yz will be 0, zx will be 0, xz will be 0, etc. So what I need to concentrate on in this problem, at least, it is epsilon x, epsilon y, gamma xy, and eventually gamma yx. These 4 components of the strain is what I will concentrate on to recall the concept of strain. So now, let me immediately ask you the question, well, what are these values? And it's good to go ahead and try to calculate these components of the strain. Try it. And I strongly suggest that if you actually face difficulties, that you go back and recall these concepts, both stress and, in this case, strain, from your study of ME 231. All right, so, well, what we will have is, let's first go ahead and talk about epsilon x and recall what a normal strain means. A normal strain means the following. You take a certain line element, let's indicate it with a dotted blue line. Say I draw a dotted blue line here at that point, which is, we're going to think of it as being attached to the original square plate. And eventually, the plate deforms and that dotted blue line will move to a different point. So every dot along that line will move to a different point. I am pulling on the plate along the y direction and I'm shearing, you see, in the along towards the x direction, and therefore every point is going to move up and to the right. So let's say that that point moves over here. And now I could have drawn, notice, this blue line for this particular example at any y location, and it would display a similar trend. That line would have moved up and to the right. So it's sufficient to concentrate on this one line. And what I observe is that every point moves up by the same amount in this particular example, and moreover, they move to the right by the same amount. In other words, the original length of the blue line before and eventually when it moves, when the plate deforms, it becomes the red dotted line. The length of the two lines, they're the same. The original length is the same as the final length. So I'm looking at the length change along the x direction, and because there is no length change, I immediately deduce that epsilon x is actually equal to 0. There is no length change. But then I can do the same thing for the y direction. Now, for the y direction, there is actually a amount of elongation by a certain amount. So a line that I draw is not going to preserve its length. Actually, it will change its length. It's going to elongate because I'm pulling along the y direction. Now notice that the length after deformation is influenced by the amount by which I shear this plate. So the original length is in the vertical direction, it's 1. After deformation, that line becomes skew to the y-axis. But let's recall this point. The way I'm going to approximate the change in the length okay, which is 5 times 10 to the minus 5, okay? That's the change in the length. It's an approximation of the real length change, but it's a very good approximation. Divided by the original length. So change in length divided by the original length, which is 1 meters over meters. It is 5 times 10 to the minus 5. So we recall at this point that the strain is unitless, whereas for stress, typically the units that we prefer are not newtons per meter squared, but because they are very large, the units are MPa. Okay, so that takes care of the length change in the y direction. So let's come to the concept of shear strain. The shear strain, remember, has to do with angle changes. Okay, so the normal strain concept works as follows. It's the new length minus the old length divided by the old length. Okay, so the shear strain is a change of the angle. Okay, the new angle is the angle that this red line makes with the x-axis. The old angle is the angle that this line, the original vertical line associated with the blue rectangle, in other words, the y-axis, makes with the x-axis. So that's the angle of 90 degrees. But remember, we indicate angle in radians when we calculate the shear strain. So the shear strain is the change in the angle. And remember, unlike the calculation of the normal strain, it's not new minus old, but rather it's old minus new, so that old is larger than new in this case. I would get a positive value of shear strain for this case, which is the preferred default way of indicating it. Moreover, there is no scaling, but the difference is taken in terms of the in terms of radians. Okay, so that's the angle that I would like to calculate. That has to do with the shear strain. Okay, now the tangent of that angle is that distance divided by this distance. Okay, but again, the way I'm going to approximate that tangent, okay, and the tangent of the angle is approximately equal to the angle itself ultimately. Because why? Because these numbers are very, very small. So tangent gamma is this value, which is now 2 times 10 to the minus 5, divided by the total length, which is going to be approximated as 1 meters over meters. Okay, and therefore the shear strain is 2 times 10 to the minus 5. Okay. So now let's come back to two issues associated with epsilon y and gamma calculation. First of all, I am saying that the angle is approximately equal to its tangent, which is approximately equal to simply this distance, not divided by the whole distance, but over 1. Okay? Well, okay, first let's calculate it divided by the, divide this value over the vertical value. Okay, so that would be 2 times 10 to the minus 5 divided by 1 plus 5 times 10 to the minus 5 meters. And this is not equal to gamma, but it's equal to tangent gamma. But 5 times 10 to the minus 5 is so small that actually it doesn't matter whether I include this term or not, and moreover, it doesn't matter whether I look at tangent gamma or gamma itself, because these are approximately equal terms, right? So for the same reason, when I was calculating the normal strain, I simply took the ratio of the length change along simply the y direction divided by the original length. Okay, so I am assuming that any deformation that we presently have in our analysis, which is a assumption that's going to hold almost all the way through our course, is that we have small deformations. And let me write that in big letters over here. We are assuming in the context of this course, with perhaps just a few exceptions, small deformations. And as a result, strains. Now, how small is a strain? How small should it be? How small should the deformation for our assumption to hold? And how important is that assumption? So first of all, the assumption is very important because almost all the formulation that we are going to follow rests on the assumption of small deformation. So how small should a deformation be to fit our assumption of smallness, to make sure that our formulation is mathematically and physically relevant? Well, that depends to a certain extent on the application that we are seeking. But what I can tell you is, for instance, a strain of the order of this amount is certainly simple, whereas a strain of the order of, say, 1, okay, that would be 100% elongation, that would be extremely large, okay? So it's certainly less than 1, and it is going to be, if it is of this magnitude, is certainly small. And in between, we eventually need to be careful when we look at the numbers and judge whether the strain is sufficiently small or not. Okay, so now that's the shear strain. Which component of the shear strain are we looking at? Well, we're looking at an angle change that is associated with the lines that lie within the xy plane. So this is gamma xy. But it really doesn't matter whether I look at the angle change between lines that lie within the xy plane or in the yx plane. In other words, I can look at the angle change between a direct line along x and y or along y and x. Just doesn't matter. It's a play of words. So the concept of angle change does not depend on the way you order the axes. Gamma xy is equal to gamma yx. And for that matter, gamma xz is equal to gamma zx and gamma yz is equal to gamma zy. So in other words, eventually, here we look at the concept of strain, which it seems just like stress, it has 9 components, but actually it is also a concept which is associated with 6 independent components. We could ultimately write it also as a matrix. I am not going to do that. I'm just going to here say that it is symmetric. Okay, so when you switch the indices, you get the same value, both in magnitude and direction. Okay. So now that we have the components, recall the components and the concepts of stress and strain, I think it would be nice to think about now how to relate the two. So if I give you the stress, can you calculate the strain? Or if I give you the strain, can I calculate the forces or the stresses that I need to apply to the original blue plate in order to induce that deformation? So that's what we're going to recall first from our study of ME 231.